All right, everyone. Well, welcome back. We are going to continue our journey with volume today. This is section 7.2b, solids of revolution using the disk method. All right, so hopefully you have this shape in the classroom. What I'd like for you to do is do the same thing we did yesterday. Pause the video for 2 or 3 minutes, talk to someone around you, and decide how would you describe this shape, or how was this shape built? So go ahead and pause the video. Okay. Hopefully you said, well, one way to describe this shape would be to add up a whole bunch of circles, right? And if it were a perfect shape, then we'd be adding an infinite number of circles, or maybe more specifically disks, right? Because they do have some depth to them. They are three-dimensional. So if I want to describe this shape mathematically, I would take an infinite sum, which would be an integral, from some point A to some point B. Those are unknown at this point. And sum up a whole bunch of disks, if you will, which would have the area of a circle, and then a teeny tiny infinitesimally thin depth dx. All right, so what is the area of a circle? Pi r squared, right? So if we like, we could write this like so. Okay. All right, let's take a look here. What kinds of things would we need in order to calculate the actual volume of this solid? And here's an important question. If you take a slice out of the solid, if I were to remove one of those circles or one of those disks, what shape would you have? And are you going to have this shape all the time? So what stays the same? What changes? Well, hopefully you said yes, we're going to have circles every single time. They're going to have this infinitesimally thin depth every time. But what changes is the radius, right? This radius changes, and it looks like in some kind of pattern, right? Some kind of formula. So if I would know the formula for the radius, then I could calculate the volume of the solid using calculus, right? So any guesses as to what that function is that produces, or that produced the radius? Is this believable as the function that produced the radius? Right, if I have this radius here, oh, let's try this again. Take one representative radius. All right, if I take this radius here, then rotate it about the x-axis, I'm going to get that slice out of this vase-looking object. Okay, anybody know what function this is, or at least what kind of function this is? It is a sinusoidal function. One way to represent it is sine of x plus 2, and I've restricted it from x equals 0 to x equals 2 pi. So let's take a look at this representation of the same solid. So here I have my function sine of x plus 2. And you can notice as I fill this up with more and more disks, it becomes more and more vase looking, right? Tilted kind of on its side. I'm going to highlight different sections for you here. You see, as I go through the shape, I always have a circle, right, with a very thin depth, so at a disk. Okay. All right, let's go ahead and calculate the volume of this solid. I know that I'm going to have the integral, so I want to sum up a whole bunch of circles. And I want to go from x equals 0 to x equals 2 pi. Okay. And I know I want to sum up a whole bunch of circles, which is pi r squared. Each circle has an infinitesimally thin dx. So here are my 3 dimensions. So 0 to 2 pi, I'm going to go ahead and pull out that coefficient of pi because that's a constant, doesn't change. Now my radius does change, doesn't it? My radius, if you will always go ahead and draw one radii for me. Okay, and then label it, let's stick with big R. Okay. My radius here, if I do top minus bottom, is going to be f of x minus 0, my x-axis here. So really just f of x. So my radius is f of x, and since that was given to me in the problem, I can just leave it like this. And then I want to square f of x, since that's my radius, dx. And that's it. Okay, that would be the setup for this solid. Okay, in your homework, you're going to be asked to actually find that integral by hand, but right now we're just going to look at setup. Okay, so let's generalize. So if I want to find the volume of a solid that revolves some function r of x, like that sinusoidal function we had, or if I want to do a vertical axis of revolutions, if I have a relation r of y, and then I want to generalize the formulas here. One important thing to note, your cross sections always have to be perpendicular to the axis of revolution. So if I go back to this example here, my axis of revolution was the x-axis, correct, which is horizontal. So my cross section, my radius here has to be perpendicular to the x-axis. So if you have a horizontal axis of revolution, you're always going to have dx's. Everything's going to be in terms of x. If you have a vertical axis of revolution, you'll have a dy. Everything will be in terms of y. All right, so let's generalize here. For horizontal axis of revolution, my formula is going to be pi times the integral from x equals a to x equals b. If you want to write the x equals in your notes too, that's totally fine. Then I'm going to take my function, I'm calling it r of x, and I want to square my function, right? Radius squared dx. Okay. If I have a vertical axis of revolution, you're going to do the same thing, just everything's going to be in terms of y, okay? So you're still going to have pi times the integral, let's call this from c to d this time. These are now what values? These are now y values, okay? Of whatever your relation is, r of y, square it, dy. All right, let's try a couple more examples. We're just going to set up, and then we'll do the first one from your homework all the way through. Okay, find the volume of the solid formed by revolving the region bounded by f of x equals e to the negative x equals 0, and x equals 1 about the x-axis. All right, well, e to the x, the exponential function grows really, really fast, right? And it looks like that. So if I stick a negative on the inside of that parent function, it's going to flip about the y-axis. So my function, let's get a different color. My function is going to look something like this. And it gets closer and closer to the x-axis. Okay, so that's my function f of x. I also want to use the line x equals 0, which is the y-axis, and x equals 1. We'll say that's right here. Okay, so I want to take this region right here and rotate it about the x-axis. Okay, so horizontal axis of revolution, right? I want to rotate it about the x-axis. So dx or dy? That'll be dx horizontal. So draw your representative, pick out one radius there for me. That's going to be capital R. Okay, so now we just go by our formula. We're going to have pi. From x equals what to what? Well, from here to here, which we said was 0 to 1. Here's my radius, so do top minus bottom, so the black function minus the x-axis, so f of x minus 0, which is just going to be f of x squared dx. And if the problem is asking for setup only, it's completely appropriate to leave it as f of x, because that's what the authors of the problem called that function. All right, let's try one. Let's try another. It says find the volume of the solid formed by revolving the region bounded by the graphs of y equals x cubed, x equals 0, and y equals 0, and y equals 1 about the y-axis. Okay. By the way, notice in my previous example, let's go back for just a sec. I didn't really worry about what that final picture looked like. It really doesn't matter if you can see the final shape or not. Can you picture this being revolved about the x-axis? Maybe kind of looks like a horn, yeah, or like a speaker. If you want to go to this website here, you can kind of play with that shape and take a look at what it looks like. But again, it's not necessary to be able to visualize these three-dimensionally in order to find their volumes. Okay, so let's go back to this one. We have the graph y equals x cubed. So that guy is that squiggle. It's increasing on its entire domain, goes from concave down and switches to concave up at x equals 0. I also want to use the graphs x equals 0, y equals 0, and y equals 1. Let's call this 1. Okay, and I want to revolve about the y-axis. Okay, so here's the axis I want to revolve about. This is the region I want to revolve. Can you picture what this would look like if I were to revolve this region about the y-axis? It'd be kind of a bowl-looking shape. Again, it's really not necessary that you're able to picture that in order to find the volume. Okay, so you're going to start at your axis of revolution, go perpendicular out to your function, and this is going to be your representative radius, right? You're going to have a whole bunch of circles that go like this, around and around. Okay, so go to your formula. You're going to have pi times the integral, and are we going to have dy's or dx's this time? This time everything's going to be in terms of y, right? Because you have a vertical axis of revolution. So these guys need to be y values. So we're going to go from 0 to 1, y equals 0 to y equals 1. And then I want to take my radius squared. Now, my radius, we know that this is going to be dy. So my radius has to be in terms of y. So I can't put in x cubed, can I? Because that will be in terms of x. So ideas on what I could do. I could simply solve for y. So if I have y equals x cubed to find what x is equal to in terms of y, how could you solve for x? Just take the cube root of both sides, right? By the way, no plus or minus when you have an odd root. If you prefer to write it as y to the 1/3, that's totally fine. So I'll have y to the 1/3, that's my radius. And then I need to square my radius, right? And that's it for the setup of that problem. Okay, let's go ahead and do the first one from your homework, I believe it is. Page 465, number 1. Okay. We want to, the function we're given is negative x plus 1. And our boundaries are x equals 0 and x equals 1. And I want to revolve about the x-axis. So is that going to be dx or dy? That's going to be dx, meaning everything's going to have to be in terms of x's, yeah? So follow your formula. You have pi integral from a to b of your function in terms of x squared dx. Okay, so your a value is 0 right here. Your b value is 1. And your function is negative x plus 1 squared dx. Okay, now we want to actually calculate the volume of this by hand, no calculators. So you have a couple options to find this integral. Ideas? The two ideas I see, one would just be to expand this, which I think is the route I'm going to go. You could also do a u substitution. Let u be this inner part here, negative x plus 1. Then du would be negative dx, so you just have to account for that negative. Then just be sure you switch your limits here to u values. Okay, either way. I think I'm just going to go ahead and expand. So we're going to have pi times the integral from 0 to 1 of negative x squared positive x squared minus 2x plus 1 dx. Okay, now to find this integral, we need an antiderivative. So x cubed over 3 minus x squared plus x, evaluated at 0 and 1. If I plug in 1, I'm going to get 1/3 minus 1 plus 1. If I get 0, I'm going to get 0 minus 0 plus 0. So inside the brackets, I just get 1/3. So my answer is pi times 1/3, or pi over 3. Okay, that is it for this lesson. Tomorrow we're going to look at the washer method. But I just want to reiterate that calculating these volumes are all about being able to figure out what one slice is. If you can't visualize the final picture, the final shape, but that's really okay. As long as you can write in one slice, you're going to be able to calculate the volume of the solid. So if picturing 3D shapes like this is not your forte, don't freak out because you can totally still figure out all the volumes. All right, good luck with this lesson, and I will see you all next time.